This is a solution to the problem titled Wrecking Ball at Ralph. In this problem, we are focused on the tension at multiple points within a wrecking ball and chain system. To help our dear friend Ralph, we are asked to calculate the maximum tension, minimum tension, and tension at a point 3/4 of the way up from the chain. The problem states that Ralph is on a school field trip and notices a large wrecking ball hanging from the ceiling. As a curious physics student, he wonders how much tension is being placed on the chain. He was informed that the weight of the wrecking ball is 65 kilograms and the weight of the uniform heavy-duty chain is 25 kilograms. Because we are focused on tension of something hanging completely vertically here on Earth, we can account for the acceleration of gravity, which is 9.81 meters per second squared. First off, we are interested in finding the maximum tension of the chain. We can use Newton's second law that states force equals mass times acceleration. In this instance, the force of the system can be indicated using Tmax to represent maximum tension. Mass can be expressed with the weight of the wrecking ball plus the weight of the chain, and acceleration can be indicated using the acceleration of gravity on Earth. To find the maximum tension, we must first identify the object of interest. In this case, it is the topmost link in the chain hanging from the ceiling. As always, it is helpful to draw a force diagram at our object of interest. At the topmost link of the chain, we have tension pulling directly upward and the weight of the wrecking ball plus the weight of the chain pulling directly downward. We can then plug in our known variables in the equation for maximum tension. The mass of the wrecking ball is 65 kilograms plus the mass of the chain, which is 25 kilograms. The sum of both masses can then be multiplied by the acceleration of gravity, which is 9.81 meters per second squared. This results in the maximum tension of the chain being 882 newtons. We know that our units of tension are in newtons due to the kilograms times meters over second squared. Next, to find the minimum tension, our object of interest in this case is the bottommost link in the chain. Again, we draw a force diagram at our object of interest. After drawing our force diagram, we can see that we have tension pulling directly upward and just the weight of the wrecking ball pulling directly downward. Here we can modify our tension equation to account for just the mass of the wrecking ball and the acceleration of gravity. Take a second to pause the video and plug in our known variables to calculate the minimum tension of the chain and continue watching when you are done. Great. So hopefully you're able to plug in 65 kilograms for the weight of the wrecking ball and 9.81 meters per second squared for the acceleration of gravity. This results in a value of 637 newtons. This value makes sense because it is lower than the value for the maximum tension of the chain. Since our object of interest is the bottommost link in the chain, we can omit the weight of the chain and only focus on the weight of the wrecking ball. Lastly, Ralph wonders what the tension would be at a point 3/4 of the way up the chain. For our force diagram, we have tension pulling directly upward and the weight of the wrecking ball plus 3/4 of the chain's weight pulling directly downward. Take a moment here to pause the video and modify the equation for tension at our object of interest. Alright then, so here we have a similar equation to what we used to solve for maximum tension. However, we are only accounting for 3/4 of the chain's weight. Plugging in 65 kilograms for the mass of the wrecking ball, 25 kilograms for the mass of the chain, and 9.81 meters per second squared, the tension results in a value of 821 newtons of force. These calculated values make sense because we can see that the maximum tension resulted in a value of 882 newtons, which is larger than 821 newtons for the tension 3/4 of the way up the chain. And this value is larger than the minimum tension of the chain, resulting in 621 newtons. Now Ralph can go home and finish his mastering physics homework. What a great student!